Good morning everyone, Dr. Nat here. So we are continuing with our module number 11. This is going to be the last part and also the last part that is going to be covered in your exam as well. So I think this is good news. We are almost finishing our syllabus. As I mentioned to you before, I was on the fence about adding linear regression to the syllabus, but I think I'm going to skip that for our semester, because there's not much time and I don't think it's going to be meaningful if we did it very fast. Okay, so I'm going to continue with this part. So we have talked about the difference in the mean. We have talked about the difference of the sample proportion. We have talked about the relationship of confidence interval with the hypothesis testing, and we know what is significance level, which is alpha. And now we are going to go for the last subtopic, which is about the type 1 and type 2 errors. But before we can talk about the errors, we need to know these two things, which is the critical point and also the rejection region. So the critical point, what is that? It is a value of the test statistic that produces a p-value that is exactly equal to alpha. So we know what alpha is. Alpha is the significance level, and the critical point is telling us that the p-value is exactly equal to alpha. So we'll see what that means. And then it will become a dividing line for the test statistic, just as the significance level. So it's not exactly alpha, but it's going to be a line that we will not shift around after we have found out. Okay, and then we are going to talk about what is rejection region. It is the region on the side of the critical point. Let's say your critical point is this line 1361.5. So the rejection region is this region over here, the region on the side of the critical point that leads to rejection. Again, remember, we are going to reject the null hypothesis if the p-value is less than our significance level. If our significance level is 5% and our p-value is something that is less than 5, we would say, okay, it's too small, we're going to reject the null hypothesis. So this is the rejection region that tells us that we should reject the null hypothesis. Okay, so the critical point itself is also in the rejection region, which means that the critical point is part of the rejection region itself. So this line is together as a region. So here you would see that instead of using the z-score, we are using 1361.5. And this is calculated by mu. This is going to be our mu. Remember, the mu is going to be corresponding to the highest point of the normal distribution. And our critical point is the mu plus the z-score times with the sample standard deviation. Now, what is the z-score? The z-score is determined based on your significance level. Let's say you want it to be 5%, then your z will be 1.645, assuming that this is a one-sided confidence interval. So if you were going for a two-sided confidence interval and your significance level is 5%, then that would be 1.945 if I'm not mistaken. Remember the z alpha over 2 for 5%. So it's exactly the same z as we talked about in the confidence interval, but for this one we need to know the exact value for our critical region, and then we have to decide what is going to be our rejection region. Okay, so we'll talk more on this, and later on we're gonna see more of this in the example. Alright, moving on. So when we have already know what is our critical value or our critical point and also our critical region, our rejection region, we can find out what is our type 1 and type 2 error. So sometimes after making a decision using the hypothesis, there is a chance that the decision could be wrong. Remember that we were talking about when we had a p-value of 4.99, but you are a firm believer of the 5% significance rule, therefore you reject it. But when you tried to resample it, you found out that, oh, the p-value is 6 instead of 4.99. So that happens when there is error, when the error is high. So how do we find out what is the error of our hypothesis? So this is how we do it. So to summarize type 1 and type 2 error, when conducting a fixed level test, meaning to say hypothesis test, at significance level alpha. Again, we can choose alpha to be anything. It can be 1%, 5%, 10%. There are two types of errors that can be made. These are the type 1 error, whereby you reject the null hypothesis when it is true. And then the type 2 error is you are failing to reject the null hypothesis when it is false. So the type 1 error occurs when the null hypothesis is true but you reject it. So type 1, you associate this with true. You go for true. And then for type 2, the null hypothesis is false, but you didn't reject it even though it's false. So this is the way that you can remember it. And the type 1 error is very easy in a sense that it cannot be it is equal or less than alpha. So type 1 error is almost always less than alpha or equal to alpha. So type 1 error is very easy. You can minimize it by decreasing your alpha. If you want to increase your type 1 error, I don't know why you would want to do that. You can increase your alpha and increase your type 1 error. So let's say my type 1 error is 5%. Therefore, my probability of making the type 1 error would be 0.05. And if I change this alpha to become 1%, my type 1 error would be 0.01 or less. So the probability of type 1 error is never greater than alpha. Yes. So it is important to make these two errors reasonably small. So how will you do it for your project? So you have to find out what is the error for your hypothesis. So again, type 1 error, we're going to discuss more on this. If alpha is the significance level that has been chosen for the test, then the probability of type 1 error is never greater than alpha. The probability will never be greater than alpha. So assume that we are testing this null hypothesis, whereby the sample mean minus the sample x mean minus, let's just call this the difference between the sample means, is less than or equal to 0 versus the alternate hypothesis, the difference is greater than 0. So this is just our hypothesis, it's random. At a fixed level of alpha equals to 0.05. This value we just decide on our own. This is what we want to do with. This is what we want as our alpha. You can change it. A type 1 error will occur if we reject the null hypothesis, but it is true. Remember, a type 1 error will occur if we reject the null hypothesis when in fact it is true, which will occur if the probability is less than or equal to 0. P-value. So if our p-value is less than 0.05, we know that we need to reject the null hypothesis. So which in turn will occur if the sample mean is greater or equal to 1.645 standard deviation of the sample mean. So here your mean is equal to 0, so your normal distribution is going to be 1.645 times with the standard deviation. So if our mean is not equal to 0, for example, it was 1350 that we saw earlier, and a 5% significance level would correspond to 1350 plus with 1.645 because it is the z for 5%. And then we would want to know what is our population standard deviation divided by the square root of the sample size. So this would be the value, whatever this is. Okay, so this would be our critical point or the critical value. I'm going to call this the critical point. And the region that is beside the critical point will be our rejection region. Okay, so we are going to reject our null hypothesis if our sample mean is within this rejection region. And where is that? It is going to occur if the sample mean is greater than 1.645 standard deviation of the population divided by square root of n. Why is it just this value? Because our mean is 0. So it's just this. It's easier. So consider the case where our mu is equal to 0. So this is our first case first. Okay, so let's consider the case where mu is equal to 0, which is exactly this. So when mu is equal to 0, the probability of the sample mean being greater or equal to the rejection region, which is 1.645 standard deviation of the sample mean, is equal to 0.05. This is the probability, right? How do we know the probability? It's just the significance level that we have decided. It's going to be exactly at the critical value, and the critical value tells us what the rejection region is. It's exactly that. What happens if we shifted the mu to become less than 0? So what will happen to the distribution? So we make a point to not change this critical value. Let's fix it at this point, and I'm going to shift my distribution to the left because now my mu is over here. It's a negative value. I don't know what it is exactly, but this is what we're working with. So if I were to draw this very poorly, I would see that my rejection region has now decreased. Assuming that I still use the same critical point as my critical point, my rejection region, however, has decreased because now it does not cover this part. So now when my mu is less than 0, my probability of having the sample mean in the rejection region is going to be less than 0.05, because it's just common sense, right? We're shifting the distribution, but the critical value remains. Therefore, our rejection region also decreases. The probability inside that region is decreasing. So the probability of rejecting the null hypothesis and making a type 1 error is going to be equal to 0.05 or less. It's not going to be any more than our significance level. Okay, so what is type 1 error again? Type 1 error is you rejecting the null hypothesis. You are rejecting the null hypothesis even though it is true. So they are saying that this is the error for you to reject the null hypothesis even when it is true. The probability of you rejecting it wrongly is going to be 0.05 or less. Why? Because we are considering when our sample mean is going to be inside the rejection region, and that is when we would reject our null hypothesis, right? So they are calculating for that. Okay, and then we are moving on to the type 2 error. So we can minimize type 1 error by simply changing our significance level to become 1%, 3%, and it would be equal to that or less, right? So the smaller we make the probability of type 1 error, the larger the probability of the type 2 error becomes. So you can't win both, but you can try to minimize both. So what is the strategy here? We need to choose a value alpha that we are comfortable with. For example, 5%, or 3, or 10, but 10 is quite high actually. Choose a value for alpha that is reasonably small to minimize type 1 error, and then you compute the type 2 error. So you can't choose type 2 error and then go to type 1 error. So the first step is for you to declare what your alpha is, and then you see if your type 2 error is high or not. If it is high, then you would have to redesign the experiment. Okay, so type 2 error is related to power. So power of a test is the probability of rejecting the null hypothesis when in fact it is false. So power is given by 1 minus P, the probability of making a type 2 error, which is this probability. So we would want a high power. Because a high power would indicate a small probability of a type 2 error occurring. So our goal is to have high power or low type 2 error, small type 1 error as well. Okay, so to be useful, a test must have reasonably small probabilities for both type errors. Therefore, we would want a high power to have a small type 2 error. So how high is high? The question that we have asked ourselves for the significance level before. So it can be 0.8 to 0.9. This is, again, there's no scientific validation for this value, but we will go with it because it is convenient. So note that power calculations are generally done before the data is collected. So you have several things that you have to do before you can actually analyze the data. The first thing is to form your hypothesis, determine what your alpha is, and then calculate your power, and then analyze your data, relate it with the confidence interval, and then make your conclusion. So I will write this up in an instruction for your project after this. So computing the power involves two steps, which is computing the rejection region. We have seen this earlier. And then number 2 is to compute the probability that the test statistic falls in the rejection region if the alternate hypothesis is true. So for type 1 error, we were not interested about the alternate hypothesis. We were just trying to find out what was the probability of our sample mean falling into the rejection region. And we found out that the alpha is going to be equal or less than the alpha. Great. But for the power, it's a little bit I would say messier, because we are now trying to find out if the z-score falls in the rejection region if our alternate is true. Previously, we have been assuming the null is always true, and then we would reject it if it's wrong. But now we are testing the alternate instead. So this is power. Okay, so let's go for an example. Assume that a chemical process has been developed that may increase the yield over that of the current process. So the current process is known to have a mean yield of 80. Whoops. And a standard deviation of 5, where the units are the percentage of the theoretical maximum if the mean yield of the new process is shown to be greater than 80. So we are going to see if the new process is greater than 80. If the mean yield of the new process is shown to be greater than 80, the new process will be put into production. So let mu denote the mean yield of the new process. It is proposed to run the new process 50 times, so our sample size is 50, and we want to test this hypothesis at a significance level of 5% or 0.05. So now they want to know if the mean yield of the new process is shown to be greater than 80 or not. So this is what we're trying to answer. So this would typically be our alternate hypothesis, and our null hypothesis would be less than or equal to 80. So this is what we're testing at a significance level of 5%. Our standard deviation is 5, and this is our sample size. Now we would want to calculate what is our z-score. We are dealing with one-sided hypothesis test, right? And our alternate hypothesis is greater than, so we are going to see on the right, our p-value is going to be on the right, and then our significance level is 5%. The z-score for that is going to be 80. I'm going to have to calculate the standard deviation of the sample mean, which is s over square root of n. Okay, fairly straightforward here. 5 over square root of 50. I don't know what that is. Let me just use my calculator. Okay, square root of 50. 5 divided by that. So it's going to be 0.707. So 0.707. And then what else do we need? We want to know the z-score. Yeah, I think we're okay now. So to calculate power, let's go back to the definition. To calculate power, we will try to find out the probability, we need the z-score, that the test statistic falls in the rejection region if the alternate hypothesis is true. So now we have to assume our alternate hypothesis is true for power. So if our alternate hypothesis is true, then mu can be something, any value that is greater than 80. So I'm going to choose the one that is closest to the null hypothesis. No reason, just want to choose that one. So let's go for that. So sample size is n equals to 50, significance level 0.05. This is our hypothesis. We are assuming our alternate is true for power, specifically for power. So we must now find an approximation for our standard deviation. In practice, this can be a difficult problem because again, power is calculated before you get the sample. So how do you approximate that, right? So because the sample has not yet been drawn, there is no sample standard deviation, but we're going to assume with a convenient value. So here I'm going to assume it's 5 based on what they have told me. Kind of cheating, but acceptable. So the null distribution follows a normal distribution. So this is mu. This is if we are assuming the null hypothesis is true, right? But we will test our alternate hypothesis. So the H0 is true, so mu is 80, and this is going to be our variance. How did we calculate the variance? It was 0.707. If this is our standard deviation, so variance will be squared of that. So the critical point has a z-score of 1.645. This is corresponding to 5%. So mu plus with, we're going to look at the right side, right? So mu plus with the z times with this guy over here that we already calculated. So this would correspond to mu is 80 plus with 1.645 times with the standard deviation 0.707. What does this give us? This gives us the critical point. This gives us the critical point. Okay, so the critical point follows the null distribution values. After we have found the critical point, we would test the z-score using the alternate hypothesis values. So using this equation, I found out that my critical value is going to be 81.16, and if my sample mean is greater than this critical value, then I would have entered the rejection region greater and equal to this value. So the rejection region is sample mean greater and equal to 81.16. So the first two things that you need to do before you can calculate power is finding out the critical point. How can you do that? You need to know what is your mu using the null distribution, and you have to find out what is your standard deviation sample mean and find out what is the critical point, and then from there find out what is your rejection region. The next step would be to compute the power, whereby it is the probability that the sample mean will fall into the rejection region. Now we have assumed that previously we have assumed that the null distribution is true, which it means that the mu is equal to 80. But if our alternate hypothesis is true, we need to assume that our mu is not going to be 80 but something that is greater than 80. So for example, 81. So now to calculate my z-score, it will become the critical value minus the mu of the H1, which is the alternate hypothesis, divided by our standard deviation, the same standard deviation, which is 0.707, and you would get the z-score as 0.23. And using your CDF table, you would find out that the probability of the area to the right of the critical point would be 0.4090, which corresponds to 40.90%. Now you would think that this value is high because we were dealing with like 0.1, 0.2 or like 3%, which is very, very low. But in reality, this value is low because we want a high power. Remember what was the definition for power? It is the probability of 1 minus the probability of type 2 error occurring. So if our power is 40.9, it means that our type 2 error is basically around 60%, quite high. So this is not something that we want. We want our type 2 error to be small. So a power of 0.4090 is very low. It would be unwise to invest time and money to run this experiment since it has a large chance to fail. Type 2 error, the probability of type 2 error occurring is close to 60%, very high, which means that we are going to accept the null hypothesis even though it is false for type 2, right? So this is not what we want. If it has a high chance of occurring, then we know that our experiment is not great. So here, this is a table, this is the plot of the null distribution versus the alternate distribution, which is what we saw for the z-score, right? So first, for the null distribution, we found out what was the critical value. This is using the null distribution. Everything was the same, just finding out what was the critical value and the rejection region. And then using this value of the critical point, we find out what is the probability of it falling into the rejection region if the alternate distribution is true. And this would mean something that is greater than 80. And then you would calculate that probability, and it corresponded to something as 40.9. Okay, so the z-score under the critical point follows the null distribution, which is 1.645, the typical value for 5%. And for the z-score is 0.23 under the alternate distribution. So it was the critical value minus the mu when our alternate hypothesis is true divided by the standard deviation. Z-score would be 0.23. So you would see that the rejection region has increased. Right? The rejection region has increased. Okay. So we chose a mu to be 81 under the alternate hypothesis. What would happen if we chose a slightly higher value than 81, which is, for example, mu is equal to 82? So the z-score under the alternate hypothesis for the critical point 81.16 would be the same step as we have seen before, which is 81.16 minus the mu, which is under the alternate hypothesis, minus 82 divided by 0.707. Then you would get your z-score as minus 1.19, and this would correspond to a probability of 0.8830. This is your power. Remember, you want a high power, which means that you would get a small type 2 error. So this is going to be acceptable. So what can we conclude from these two means that we have chosen? One was 81, which was the alternate hypothesis. 82 was also the alternate hypothesis. So we chose two different values and they gave us two different results. One, the power was low, and the other one, the power was high. So the alternate distribution is obtained by shifting the null distribution. The power depends on which alternate value is chosen for mu. So you saw that just now, if you chose 81, your power is high. If you chose 82, your power is high. If you chose 81, your power is slightly low, and can range from barely greater than the significance level all the way up to 1. So your power can only go from alpha up until 1. So if the alternate mean is chosen very close to the null mean, we have seen this when we chose 81, the alternate curve will almost be identical with the null. So this is my null, and my null is 80. If I chose it to be 81, it's going to be only slightly shifted, and it's almost overlapping, but not really. What they're trying to say is it's going to be close to the null distribution. Therefore, the power will also be close to the alpha. If the alternate mean is far from the null, and we have seen this when we chose 82, almost all the area under the alternate curve will lie in the rejection region, and the power will be close to 1. So let's look at this one. Almost all the area under the alternate distribution will be in the rejection region, which is what we want actually. And the power will be close to 1. When the power is not large enough, it can be increased by increasing the sample size. So we will see how we can increase the sample size. in the following example. So based on the null distribution of our sample mean, this is the critical point that we have calculated just now. It's the same example, we're just finding out the sample mean. So we are saying that our sample size is unknown. Remember, when we are calculating power, we do this before we sample. Before we sample from the population. So n is unknown at this point. So the power of the test is the area of the rejection region under the alternate curve. We decide that this area must be 0.9. So again, you can be a firm believer of 80% power, or you can be a firm believer of 90%, you can be a firm believer of 85, depends on you. But you have to define this at the initial point of your experiment. Therefore, the z-score is going to be z equals to minus 1.28. So the power of the test area is the area of the rejection region under the alternate curve. We decide that this area must be 0.9. Therefore, remember, our critical value tells us the rejection region. The critical value tells us the rejection region. If we decide that this region must have a probability of 0.9, then our z-score would be minus 1.28. Let me look at the CDF table really quickly. Okay, so I've pulled up the CDF table, and if we want our power to be 90%, which means that the rejection region should overlap 90% of the alternate distribution. Let me show you the graph. We want this side to be 90%, which means that this guy over here should be 10%. So if we are going to look at our CDF table, we need to find out the z value, which corresponds to a probability of 0.1. 0.1 would correspond to this guy over here, which is minus 1.28. Minus 1.28 gives us a probability of 10%. Okay, so because we chose this to be 90%, our z-score is minus 1.28. Therefore, we can now find out the critical point for this, which is 81 minus 1.28 times with 5 divided by the square root of the n. Now, this is under the alternate distribution, and this would be under the null distribution. So we are going to equate these two equations and find out what is our n. So using our fancy calculator, we find out that the sample size is 214, and this is the sample size that we need from our population to ensure that our power is 90%. Again, it doesn't have to be 90%, it depends on you. We have limited data, so do what you must, and if you have a high type 2 error, justify why it happens. Okay, so this is the end of our lecture and also the end for our syllabus. So I just want everyone to know that just do your best, it is always enough, and I will be available if you have any questions up until your exam day. So take care everyone, and I'll see you in the WhatsApp group. Bye bye.